Hi friends, our next topic is electromagnetic waves. You know that changing magnetic field can give rise to electric field, right? Now the question is the converse possible? I mean, can a changing electric field give rise to magnetic field? Maxwell is the guy who said that this is indeed possible, and he did some experiments and gave us some equations. Those are known as Maxwell's equations. They express the basic laws of electromagnetism. Now let's go into the topic. Electromagnetic waves. As the name indicates, there is electricity and magnetism in this. Electromagnetic waves are nothing but they are a combination of electric field as well as magnetic field. To be formal, they are coupled time varying electric and magnetic fields. Those are known as electromagnetic waves. And it so happened that the speed of electromagnetic waves turned out to be very close to 3 into 10 power 8 meters per second, which is the speed of light, which is measured from optical instruments. So this led to a remarkable conclusion that light is an electromagnetic wave. This is the experiment done by Maxwell. These are two capacitor plates, and here is a wire, and it carries a current I, and here comes out another wire which also carries current I. So these are the directions of current. What happens here, since current is nothing but flow of charges, right? So the capacitor plates get charged. So the charge on capacitor plates increase as time passes. Now, anyways, consider this surface S1, the blue surface. By Ampere's law, the magnetic field at any point P is given by what? Uh, Let us find out using this law only. B dot dl, when integrated over the perimeter of loop, gives us mu naught times the current passing inside it, right? So current is I, okay? Now from this what I can get? Magnetic field, and the perimeter is say 2 pi r. Let the radius of that blue circle be r. So it should give me mu naught I. So what did I get the magnetic field to be? Mu naught I by 2 pi r. Well, this is fine. We got this by using surface 1. Now what Maxwell did, he assumed another surface, that pink surface which you see, which is going through the capacitor plates. Are you able to observe it? The perimeter of first surface S1 and second surface S2 is the same black line, that circle. But this surface passes in from what? The second surface passes through the capacitor, the cup-shaped surface. And note that current carrying that wire, the wire that carrying current is stopped by that plate. So no current passes through the pink surface. Are you getting me? So when I apply what Ampere's law for the same perimeter of surface S2, what will I get? B dot 2 pi r should be equal to mu naught times current is 0 right here. So what did I get? Magnetic field to be 0. These are contradicting, right? So something's wrong here. Observe one thing. There is no current passing through the surface S2. But what can you observe from the figure? There are electric field lines. Are you observing? They pass through the surface S2. Now, since the current increases the charges on the capacitor plates, you know that electric field lines or the electric field is proportional to the charge on the capacitor plates. So, since the charge is increasing, my electric field is increasing. Getting the point? So, since the electric field is changing, the electric flux is also changing. Let us write them, what we discussed now. Electric field inside those capacitor plates is given by Q, that is the charge on plates, by A epsilon naught. We discussed this while we were discussing the capacitors. A is the area of the capacitor plate, and epsilon naught, as you know, is a constant. Now, if this is the electric field, what will be the electric flux? It is electric field into area, right? So what will I get? 1 by epsilon naught Q by A into A, which is nothing but Q by epsilon naught. This is clear? So the flux is Q by epsilon naught. If this is flux, what will be the rate of change of flux? Let me write it as electric flux. this will be 1 by epsilon naught is constant and d by dt goes here. Rate of change of charge is what? It is the current, right? So finally I'll get current by epsilon naught. This is the rate of change of electric flux. Observe this, you have current here. Are you getting me? This can be written as epsilon naught times rate of change of electric flux. And this is what I want to prove. This current is known as ID, or this is called as displacement current. In the wire we had IC, which is the conduction current, which is caused due to the flow of charges. Here we have displacement current, which is caused due to the changing electric field. Are you getting me? And this displacement current is also called as Maxwell's displacement current. So there is no current passing from one capacitor plate to the other capacitor plate. There is no current, but there is electric field which is changing. So there is electric flux which is changing, and that is equivalent to current. Okay. Maxwell made a small modification for the Ampere's circuital law. He said that the B dot dl, when integrated over the perimeter of any surface, you have mu naught I, right? So what he said is that it's not I, just it is the sum of conduction current and displacement currents. So my total current will be the sum of conduction current and displacement currents. This is what is the modification made to the Ampere's law, and now it is called as Ampere-Maxwell's law. Now, before, in all the cases which we solved in previous chapters, we have never encountered a surface passing through the capacitor, right? So there the current was equal to the conduction current. The displacement current was zero because electric field was not changing in time in those cases. Now if you are dealing with surface inside the capacitor, there the conduction current is zero. So the net current will be equal to the displacement current only. Writing the same equation more clearly, I can write it as mu naught IC plus mu naught ID is what? Epsilon naught d phi E by dt, right? So this will be the Ampere's Maxwell's law. And through this law, electricity and magnetism are made more similar now. Observe this, before we had changing magnetic field giving rise to electric field, right? Now changing electric field is also giving rise to current, and which in turn gives rise to magnetic field, right? So they are more symmetrical. Why I am using more symmetrical that term? Because even now they are not completely symmetrical. Like you have electric monopoles, that is electric charges, but you don't have magnetic monopoles, they are always paired. So there are some dissimilarities. However, with this law, now you know all the four Maxwell equations, you can understand them. The first one is known as Gauss law for electricity. We discussed this in electrostatics, and this is the Gauss law for magnetism. You know this, and this is a Faraday's law. That and this last one is what we discussed just now. Sometimes mu naught epsilon naught can also be written as 1 by c square, where c is the speed of light. Let us solve this problem. A parallel plate capacitor with circular plates of radius 1 meter has a capacitance of 1 nanofarad. These are the capacitor plates, say they are circular, okay? And at time t is equal to 0, it is connected for a charging in series with the resistor of 1 mega ohms. So I'll connect it with a 1 mega ohm resistor and across a 2-volt battery. 2 volts, it is given as 1 nanofarad, 1 mega ohms, that is 10 power 6 ohms. Calculate the magnetic field at a point P halfway between the center and the periphery of the plates after t is equal to 10 power minus 3 seconds. So where is my point P? Halfway between the center and periphery of the plates. So halfway between the center and periphery. This is the periphery. So this will be my point P. This is the periphery, right? Okay, say this is something O, the center. This is my point P, which is at a distance half meter from O. Okay, at time t is equal to 10 power minus 3 seconds, I have to find the magnetic field at B. You know that charge varies on a capacitor plate as CV into 1 minus e power T by tau, where tau is the time constant, that is CR. If you are familiar with this equation, that's fine. If not, just accept it. This is how the charge on a capacitor plate varies. CV is the maximum charge that it can hold, and it varies like this as e power minus something. This is the time, and tau is the time constant. How to calculate it? It is CR here. C is the capacitance, 10 power minus 9 farads, and R is 10 power 6, right? So my tau is 10 power minus 3, okay? And seconds will be the units. Okay, electric field between the capacitor plates is given by charge by epsilon naught A. Okay, but this charge varies with time because current is passing in the circuit, right? Okay, let the charge be Q at some instant t, and here you have area as pi into 1 square and epsilon naught here. So you have the electric field at any moment as charge by pi epsilon naught. Well, this is fine. Now consider a loop which is of radius half meter and parallel to the plates passing through the P. This is circular loop, okay? You assume that there is a loop which passes through P and is of half meter radius. It is parallel to the plates. So that will be my Amperian loop. I want to apply Ampere's law, that is actually Ampere-Maxwell's law, to find the magnetic field. First of all, let's calculate the electric flux through that loop. Electric field into the area, right? And area will be my radius of the assumed loop is 1 by 2. So pi e by 4. This is my electric flux. Electric field is nothing but this one, right? We found it out just now. So pi by 4 times that gives me Q by 4 epsilon naught. This is my electric flux ID, displacement current, which is nothing but epsilon naught d phi e by dt, right? So epsilon naught, what is d phi e by dt? It is, let me write it clearly. Phi e is nothing but Q by 4 epsilon naught. Since the denominator is just constant, I'll get something like this, dq by dt. My charge is varying with time, right? How is it varying? At particular instant t, my charge is given by Cv into 1 minus e power minus t by tau. Cv is nothing but 2 into 10 power minus 9. This is the C and this is V. And I have 1 minus e power minus t by tau is what? Tau is 10 power minus 3. When I differentiate this with time, what will I get? I'll get it something like 2 into 10 power minus 9 into 1 is constant. So inside what do I have? E power minus t by 10 power minus 3, and I have minus into minus plus. So finally I'm going to get dq by dt as 2 into 10 power minus 6 into e power minus t by 10 power minus 3. It is just a normal differentiation. At the given instant, that is t is equal to 10 power minus 3 seconds, what will this one be? It will be equal to 2 into 10 power minus 6 into e power minus 1. Got it? And this value I'm going to substitute in this equation, for dq by dt. What is my ID? It is 1 by 4 dq by dt, right? What is dq by dt? We just found it out to be 2 into 10 power minus 6 and e power minus 1. So finally what will I get? 0.5 here. So it is 0.5 into 10 power minus 6 and e power minus 1. You just calculate it. You will get it something to be, of course, this is the ID, right? Okay. My magnetic field B and the perimeter is 2 pi 1 by 2 for the assumed Amperian loop. So this should be equal to the mu naught times what? Total current, right? IC plus ID by Ampere-Maxwell's law. Here IC is nothing but 0 because we are inside a capacitor. And finally what will I get? Mu naught times the ID, that is 0.5 into 10 power minus 6 into e power minus 1. So finally I'll get my B to be, you just calculate it, it will be 0.74 into 10 power minus 13 Tesla. It's just calculation. Hope everything is clear. In the next video I'll tell you some more details about electromagnetic waves, their sources and behavior. This is it for this video. Keep watching.